of our system dynamics and control. So we are continuing the basic concepts, and also we'll start classical method in this lecture. So already we are discussing the basic concepts. Let us further discuss it. So let us talk about the conceptual analysis of rotor angle stability. Already we discussed the definition of rotor angle stability, frequency stability, and voltage stability, and how they are classified into various like small signal, small disturbance, large disturbance, short term and long term stability aspects. We little bit discussed, and today we will discuss the conceptual analysis of rotor angle stability. What actually rotor angle stability is? When two or more synchronous machines are interconnected, the starter voltages and currents of all the machines must have the same frequency, and the rotor mechanical speed of each is synchronized to this frequency. Therefore, the rotors of all interconnected synchronous machines must be in synchronization. So this already know. This is under normal operation. Generally, all the synchronous machines, they are synchronized with each other, and they're feeding power to the grid, and their starter voltage and currents, they must have the same frequency, or else they cannot be synchronized. We know this from the very basic study, right? An important characteristic that has a bearing on power system stability is the relationship between interchange power and angular positions of the rotors of the synchronous machine. So this is very important when we study the power system stability. It's a very important characteristic when we study the interchange power, how it is looking, whether it is oscillatory or whether it is diverging, right? And it will depend upon the angular positions of the rotors of the synchronous machine. So we'll see everything how it is. So let us consider here two machines. They are connected together through a transmission line. Okay, this is your line, transmission line. And if we'll draw the equivalent circuit of these two machines, two synchronous machines, one is a synchronous generator and other one is a synchronous motor. And if we'll draw the equivalent circuit of these two synchronous machines, which are connected through a transmission line, right? And we'll see that XL is the transmission line reactance, XG is the steady state reactance of the generator, EG, and the terminal voltage of EG is ET1, let us say, and terminal voltage of the motor, let us say ET2, and XM is your steady state reactance of the synchronous motor. So if we'll plot the Phasor diagram of all these voltages, neglecting the resistances, considering only the reactances, we'll see the phasor will look like this. We will consider ET2 as the reference phasor, and with respect to ET2, where ET2 is the terminal voltage of the motor, right? So with respect to ET2, if we plot other phasors, of course, we'll find ET1, then EG, right? And EM also, right? So of course, EM will lag by delta M, and ET1 will lead by delta L, and EG will lead ET1 by delta G. So now if we'll consider the angle between EG and EM as delta, let us say it is delta, and then your delta will be equal to delta G plus delta L plus delta M. Okay. So now if we'll plot the power versus delta characteristic, it will look like this because it has a sinusoidal feature. We know we'll see the derivation of the power later, but we know that power is P max sine delta, right? Whatever power is delivered from the generator to the motor, if delta is the angular difference of the rotor angles between synchronous generator and the motor. Then if we'll plot P versus delta, it will look like this, right? And now if we want to find the equilibrium points, of course we can find it, the equilibrium points. If we'll plot the mechanical power, that is mechanical power fed to the generator, then we'll get two equilibrium points. One is here, another one is here, right? Because where PM is becoming equal to your P, right? This is P. This is your P. Okay, so these are the two equilibrium points. So equilibrium points are those points where actually the mechanical force or mechanical torque becomes equal to the electromagnetic torque developed in the system. So now we are getting here two equilibrium points. Now the question is whether these two equilibrium points are stable or unstable. So of course this is a big question. So now if we mark point A and point B, of course just by superficial analysis we can conclude that point A is a stable equilibrium point and point B is an unstable equilibrium point. Okay. So why point A is stable equilibrium point and why point B is unstable equilibrium point? Let us see. Suppose your operating point is lying at point A. Now your system is operating at point A. Now you give a small disturbance here. Okay. If we give a small disturbance, what will happen? Suppose we reduce the load on the system. Then what will happen? When you reduce the load of the system, your PM is constant, right? And your P will become because under steady state condition PM equal to P. Okay. Now your mechanical load is decreased. Okay. So now what will happen? Your PE will become greater than PM, right? So as soon as your P will become greater than PM, then there will be an acceleration at this point. This is, let us say, delta O. Delta O, that is initial or equilibrium operating point. Now when P will become greater than PM, your because of your angular acceleration in the rotor of the synchronous generator, your rotor will increase, right? Rotor angle will increase up to few extent, right? As it will increase, what will happen? Your value of P will also, sorry, your P is here less than, I'm sorry, P is less than that condition. Because load is decreasing, so electromagnetic torque will also decrease. So your P will become less than Pm because Pm is constant here. So as it will decrease, your operating point will move to this direction, downward, right? As it will move downward, so what will happen? So P is less than Pm, so therefore an acceleration will take place, right? And because of acceleration, again your P will increase. Your P will increase, right? So as it will increase, it will gradually it will achieve again this A, position A, right? Of course, it will achieve the position A, but because of its acceleration, it will move further beyond point A. So where, let us say this is A X A Y, okay. So it will further move to point A Y, where P will become greater than Pm, and that will in fact decelerate again, okay. So your rotor angle will again, rotor movement will again decelerate, and again it will come back to its position A. And again, because of the deceleration, again it will come down. Again, like that, it will continue oscillating, right? If we'll see the characteristic of delta versus time during this disturbance period. So initially it will have a large oscillation, then gradually it will die and it will settle at point A again, right? With small disturbance we are talking about. So under small disturbance, it will gradually, the oscillation will die out and it will stabilize at point A, okay? Let us say this is your delta naught. Point A means it will stabilize at delta naught, okay? So therefore, this is, for a small disturbance, it is stabilizing to point A again. So therefore, it is a stable equilibrium point. Now, if we'll consider point B, at point B, if we'll give a small disturbance, so what will happen? This is, let us say, delta B, okay. So it's small disturbance, let us say your P became lesser than Pm. So what will happen here? As P will become less than Pm, your delta will accelerate. So as delta will accelerate, we can see from this characteristic, as delta will accelerate further, your P will reduce further, right? So as P will reduce further, again the acceleration will take the delta more and more, increased value of delta more and more, right? So therefore, rather than stabilizing, what will happen to delta? Your delta will become like this. Initially, if it is started with this, then it will increase. Your oscillation will increase gradually, and finally it will diverge. Okay, that means your system is becoming unstable at this point with little perturbation or small disturbance. That therefore this point is known as your unstable equilibrium point. Okay, so this is your unstable equilibrium point. Okay, and this is your stable equilibrium point. So this is very basic analysis, okay, in the power system, stable equilibrium point. This is what will it is explained further. So stability is a condition where the equilibrium between opposing forces that takes place, the mechanism by which the interconnected synchronous masons maintain synchronism with one another is through restoring forces. This is restoring force we are talking about, which act whenever there are forces tending to accelerate or decelerate one or more masons with respect to the other masons. So we are talking about only two masons, but simultaneously multi-mason system can also be considered. In that condition, many masons, sometimes they will form the coherent groups, and two or three masons, they will together they will move with other masons. Sometimes one mason moves with all the systems. So we'll talk about that. So under steady state conditions, there is equilibrium between input mechanical torque and output electrical torque of each mason, and the speed remains constant. If the system is perturbed, this equilibrium is upset, resulting in acceleration or deceleration of the rotors or masons according to the laws of motion of a rotating body. If one generator temporarily runs faster than another, the angular position of its rotor relative to that of the slower mason will advance. The resulting angular difference transfers part of the load from the slow mason to the faster mason, depending on the power angle relationship. This tends to reduce the speed difference and hence the angular separation. So this is like a rubber band. It forces that whenever there is angular separation, it actually draws again, it restores again back to its own original position. So these angular separations takes place because of the disturbances, various disturbance conditions. So beyond a certain limit, an increase in angular separation is accompanied by a decrease in power transfer. This increases the angular separation further and leads to instability. Okay, beyond certain limit, it becomes unstable. For any given situation, the stability of the system depends on whether or not the deviations in the angular positions of the rotors result in sufficient restoring torques. When a synchronous machine loses synchronism or falls out of step with the rest of the system, its rotor runs at a higher or lower speed than that required to generate the voltages at system frequency. So it depends upon the disturbance, how how critical is the disturbance. If the disturbance is much more critical, then there is a chance of the system becoming falling out of step, and that causes instability in the system. Like here we have an analogy of cars. Suppose we have 4 cars here. We can see they're high-speed cars connected through the rubber bands. Okay, let us say these cars are connected in series in rubber bands. Okay, and they're traveling on the road. Certainly, if car 1 suddenly it increases its speed, what will happen? Suppose they're traveling in sync, and car 1 suddenly increase the speed. Then what will happen? Because all these 3 cars will have high inertia as compared to car 1, of course, because car 1 will have very less inertia as compared to combined inertia of car 2, 3, 4, because they are in sync. Okay, and therefore car 1 cannot go out of step unless the rubber band breaks. Till the rubber band is tied, car 1 cannot become out of step. Of course, it will go away, again it will come back. again it will retard and again accelerate, retard, then it will settle down. If the force of car 1 will be much more to break the rubber band, then car 2, 3, 4, and from car 2, 3, 4, car 1 will become out of step, right? It will become like it is the unstable system. So this is a beautiful analogy. Similarly, another system here, it is shown below. Car 1 and 2, they are moving synchronously together, and car 3 and 4, they are also okay. Now if car 1 and 2, they will with any disturbance, car 1 and 2, they will together move with respect to car 3 and 4 together. So this is called coherency. This coherency is maintained between car 1 and 2 and car 3 and 4. So whenever the disturbance occurs, there is a separation between these two groups, group 1 and group 2, where group 1 is consisting of car 1, car 2, and group 2 is consisting of car 3 and car 4. Okay, so this is called coherency. Okay, so we'll talk about it. With electric power systems, the change in electrical torque of a synchronous machine following a perturbation can be resolved into two components. Here, just a small thing is given. Whenever the electrical power system, there is a change in electromagnetic torque or electrical torque, it will have two components. One is called synchronizing torque component, other one is called damping torque component. So synchronizing torque component is proportional to the change in the angular deviation, and damping torque coefficient has it has a component which is directly proportional to the change in the speed, right? Like if we'll see in case of this car analogy, suppose this car will move faster, car 1, let us say, car 1, suppose let us moving faster. So the friction because of the car 1, it will act as a damping force, and that will depend upon the change in the speed, right? So that is called the damping torque. As soon as the car, because of some disturbance, car 1 moves away from car 2, 3, 4, so there is a damping torque because of the friction on the wheel of the car 1. It will act to draw back to the original position. That is the damping torque, we can say. And what is synchronizing torque? Synchronizing torque is based on the driver. If the driver wants, he can reduce the speed to synchronize with other three cars. That is the synchronizing torque, right? So here also the same two components are mentioned. System stability depends on existence of both components of torque for each of the synchronous machine. Okay. Lack of sufficient synchronizing torque results in instability through an aperiodic drift in the rotor angle. We'll see how it is. On the other hand, lack of sufficient damping torque results in oscillatory instability. One is aperiodic drift. I will show it through the figure demonstration we can see here. So the stable system is one where we have positive TS and positive TD. Okay, we can see here in this figure. Delta TS is positive, delta TD is positive, right? And hence we have a oscillatory, but it is stable. Okay, delta is stable, okay, stabilizing. But it becomes non-oscillatory instability, aperiodic non-instability, when your TS becomes negative and TD is positive, right? And similarly here also it becomes oscillatory instability like this. It will gradually, the oscillation will increase more and more, right? So that is because of the negative TD. That means your damping torque is negative. Under that condition, it becomes oscillatory instability. So these are the three cases shown here, right? Case 1, case 2, case 3. This is aperiodic unstable, right? Instability. And this is your oscillatory, but gradually the oscillation is increasing. But case 1 is stable, but oscillatory, but stable. Gradually the oscillation is dying out. Okay. So let us little bit talk about the conceptual analysis of voltage stability. A little bit we can discuss, then further Professor Siva Subramanian will talk about this more elaborately. Okay, we'll consider here a single machine system which is connected to a load, right here. So your load is your ZLD, okay, and the power delivered to the load is PR plus JQR, and the terminal voltage is VR. And the transmission line impedance is ZLN. So if we'll write the expression for current I is equal to ES by ZLN plus ZLD, obviously, right? So ZLN, if we'll write in Phasor form, it will be ZLN theta, and ZLD will be ZLD phi. Let us say the theta and phi are the phase angles of the respective impedance component. And if we'll want to find the magnitude of current, then I will be equal to ES by this whole ZLN and ZLD square root, right? And if we little bit manipulate it and take ZLN out of this equation, we'll find 1 by root F ES by ZLN. So where F is nothing but 1 plus ZLD by ZLN square plus twice. Just by manipulation, we'll get it, right? And hence, if we'll find VR will be equal to ZLDI. That is equal to, obviously, if we'll substitute I, we'll find 1 by root F ZLD by ZLN ES, and which will give us PR, that is the real power supplied at the receiving end to the load is VR I cos phi. If we'll substitute VR and I here, we'll get this expression. And from this expression, if we'll plot the power versus ZLN by ZLD, this is, we can say, the per unit power, that is PR by P max versus this Z load. Okay, if we'll increase the load gradually, what will happen? We can see the figure here. Your voltage after this critical point, it will drop down, right? Okay. So this is actually, this is not voltage. This is power curve. This is your voltage curve, right? So after the critical point, the power at the receiving end is also decreasing, and if we'll see the voltage curve, it is also dropping down gradually, right? Okay, as we increase the load. But if we'll see the current is increasing, because the load is increasing, the current will also increase. This is the basic stability phenomena, voltage stability phenomena. So let us talk about little bit the classical methods. Analysis of power system stability by classical methods will continue in the next class, and today also little bit we can discuss. So what is classical model? I hope all of you have studied this classical method of analysis in your BTech level courses. So this is just a review of your whatever you have studied. We'll just review it. Okay. Assumptions for representing the generator by classical model. What are the assumptions we take? The first assumption we take is that the exciter dynamics are not considered and the field current is assumed to be constant, so that the generator starter induced voltage is always constant. So your exciter is remaining constant. That means the dynamics involved in the exciter is not considered. Okay. Therefore, the field induced voltage, that is generator starter induced voltage, always assumed to be constant. Then the second assumption is the effect of damper windings present on the rotor of the synchronous generators is neglected. These are the very important assumptions which are actually, when we'll consider the actual model, we'll talk about, we'll consider effect is also neglected. And the third assumption is the input mechanical power to the generator is assumed to be constant during the period of study. The whole period of study will consider the input mechanical power as constant. There is no change. And fourth one is the saliency of the generator is neglected. That is, the generator is assumed to be cylindrical type of rotor. Okay. For the sake of understanding the classical model better, the case of a generator connected to an infinite bus through a transformer and transmission line is considered here. This type of system is called single machine infinite bus system, which is very, I think, very prominent in analysis, and when we discuss particularly stability studies in BTech courses, most of the time we use this model, single machine infinite bus system, right? So this is your model of the single machine infinite bus system. In the machine, whatever assumption we have took, already it is shown. And also in the transmission line, we are neglecting here the resistance, right? In transformer also we are neglecting resistance. In synchronous model also we are neglecting the resistance part. Only we are considering the reactances of generator, transformer, and transmission line. And the machine is connected to the infinite bus. It is assumed that the inertia of this bus is infinite, very high, and the reference voltage, the voltage at the infinite bus will have always the zero angle. Okay, so this is the assumption for single machine infinite bus system. And if we'll just derive the power expression, real power expression, using this figure, you can also do it. So the real part of the complex power, it is considered, and complex power we know Pi star, right? So if we'll consider the real part, gradually eliminating the imaginary part, we found that EV infinity divided by XD dash plus XT plus XL sine delta. This is your electrical power delivered by the machine to the infinite bus. And if we'll consider P max equal to this, EV, this is EV infinite XT dot XT plus XL, then at angle, of course, angle delta equal to 90 degree, P will be P max. So therefore, P will become equal to P max sine delta. So P max is, we will have P max value when delta is equal to 90 degree. Okay. So the dynamics of a rotational mechanical system can be represented as this. So dynamics will be J of d square theta m by dt square, that is equal to Tm minus T, where J is your angular acceleration, okay, and d square theta. Theta m is your mechanical rotor angle. Okay. And Tm is your mechanical torque input, T is your electromagnetic torque developed. So the angle theta m is the mechanical angle of the rotor field axis with respect to the starter reference or fixed reference frame. Okay, we'll talk about this fixed reference frame, rotating reference frame later, but till this point you must understand that this rotor field axis because rotor field will have an axis that is rotating, right? And it is theta m is the angle, that mechanical angle it makes with the starter reference axis. Okay, starter reference magnetic axis, and therefore theta m I can write delta m plus omega mst. What is omega ms? Delta m is the angle between the rotor field axis and reference axis rotating synchronously at omega ms rps. So it is assumed that if your reference axis of the starter is rotating at omega ms, okay, and with respect to the rotating reference axis, your rotor is making an angle of delta m, then of course your theta m we can express as delta m plus omega mst. Okay. So then if we'll take the derivative of this expression, this theta m, it will be d theta m by dt, that is equal to d delta m by dt plus omega ms. If we'll take the double derivative, d square theta m by dt square, it will become d square delta m by dt square. Okay. So now if omega m, let us say omega m equal to d theta m by dt rps, okay, and d of delta m by dt, I can write it from this expression as omega m minus omega ms. Okay, then just by substituting here in case of the previous equation, j d theta d square theta m by dt square, just substituting we will get j of d square delta m by dt square, that is equal to tm minus t. So it will be j omega m d square delta m by dt square equal to pm minus p. Okay, just by multiplying omega m both sides, we'll get here j omega m, here tm omega m minus t omega, and that will be pm minus, that will become pm minus p. Okay, and just by doing little manipulation, by multiplying half of j omega ms both the side and dividing sb at both left and right hand side, we'll get this expression. And if we'll consider h, that is inertia constant, as half of j omega ms square by base mva. Okay, so this is your kinetic energy stored by base mva. That is the definition of inertia constant h. So by substituting h both the side and considering pm and p as the per unit values, then we'll find the expression here h d square delta m by dt square, that is equal to half of omega ms into pm minus p per unit. Okay, so this equation is known as swing equation, and we'll study further how this will be useful for analysis of equal area criteria, that will give us the analysis of power system stability of the system, right? So we'll talk about this from next class onwards. Okay, so we'll stop here. Thank you very much.